Hi, here we are again looking at the 3421A data acquisition and control unit. The problem with this unit is that it does not power on. Essentially, when I apply power, you hear the first click, but nothing comes on the display, and you don't hear the second relay click. So I run the diagnostics outlined in the manual, in the service manual, and they suggested that the CPU was at fault. It's the missing chip there, right in the middle. Let me see if I can zoom in so you can see it a little bit better. So it's the missing, the empty socket there, and the CPU is a standard part. It's an Intel 8039, which luckily is not an OTP part. It expects its program to be on an outside ROM. So this is the ROM hidden inside the nest of wires. Anyway, I replaced the CPU. Nothing changed. Same behavior. So I decided to be a bit more aggressive. So what I did was, having extracted the original CPU and put a socket in its place, I decided to take out the CPU and take over the functions, the processor functions, and I am using an Arduino board, the 2560. So this is the Arduino board, and this drives the bus, and you can actually see the cables connecting the Arduino to the bus. So before we go on any further, let's look at how the 3421 works. What are its major functional components? Here on the left we see the CPU. It's an Intel part, an 8039, which does not contain any built-in program ROM, so it requires an external program ROM. In this schematic we see two 8K ROMs. On my unit, this is merged to a single 16K ROM, so there's only one chip replacing the two ones. Let me move a little bit to the right, and here we see the two XRAM chips. They get power from the 12-volt battery backup, and they are used to hold configuration information for the unit. And here we have the Calibration Ram. It's rather infamous because it contains the calibration information for the unit, and it has its own battery backup, a 3-volt battery, so that this is permanently powered. This chip contains, as I said, the calibration information, so if its contents are lost, then you have to recalibrate the unit, which is expensive and probably and quite difficult because it requires specialized instrumentation. On the mailing list we see that there are ways to read the contents using some undocumented instructions, and so we can back it up, and if we need to remove the battery to replace it, we can restore its contents. And finally, on the far right we see the HPIL chip. This is a standard part. It's the ILB3 and very well documented, so we are lucky. And in fact I was also very lucky because this thing actually worked on my unit, and I tested it because as you can see, it has 3 address lines and it is connected to the data bus, and you can use these 3 address lines to select the status register, one of the 8 status registers. And I was particularly interested in status register 7 because, as you can see down there, there are 2 lines that are connected to switches on the rear panel switch, and the status of these switches is reflected on status register 7. So by flipping the switches and reading this register, I could see that the IL chip was alive and working and reporting the status of the switches. Now let's go back to the main processor. Here we see the processor address bus and data bus. It's multiplexed, it's 8-bit wide, and it uses an address latch, this guy, to latch the address and drive the address bus. So the CPU presents an address on its I/O bus, and then flips the chip enable, which is the address latch enable pin on the CPU, and that copies the address to the address bus and latches it, and then the CPU can use its main bus to drive the data bus via this component, which is not a chip. It's just a shunt. It just contains jumpers from the left to the right, and this actually can be removed for some testing. So we see the data bus going to all the chips, the ROM, the RAM, the calibration RAM, and the IL controller. Here we see some complexity. It's an LS00 chip that decides which of these two banks to enable based on the chip select and the A13 address line. On my unit this doesn't exist because A13 goes directly to the address bus of the ROM, and the chip select is connected to the chip enable, to the output enable pin. For the other chips, things are a little bit more complex. So let's go a little bit down, and we find another goodie, which is the port expander. So the port expander, actually the 3421 has two of them, is essentially a way to have lots of I/O ports, and you can see that it is getting instructions from one of these, from its input port, and it allows you to drive 4 I/O ports, read their contents or set their state, and we'll see how that. And port 4 is 3 of its pins are the chip enable pins of the XRAM, Calibration Ram, and HPIL controller. So let me get rid of this, and we see the 2 expanders. Their chip select pin is driven again by the CPU, and the top one is driven directly, the other one is driven through an inverter, so it's either the top one selected or the bottom one selected. So there's always one of the two actually active. Here we see the I/O bus, which is again connected to the CPU, and here we see the port 4, the 3 pins that go to the calibration RAM and the XRAM and the IL controller. So in order to select, to enable these chips, we need to first program the port expander. So this is the display of the logic analyzer, and I want us to concentrate on the first 3 lines. This, the yellow one, is the chip select for the I/O expander. The green one is the program line for both I/O expanders, and the top line is the 4-bit bus that controls the expanders. We see that the chip select is low, so we are selecting expander 0. Now the program line is normally high, and it goes low when we want to send a command to the expander, to the selected expander. and here we send 0100. 01 is a write, 00 means port 40, and we set them to this value 0011. Going from right to left, the first one is the HPIL enable line. We want it to be high because it's negative logic, so the HPIL chip is disabled. The second bit is 1, which corresponds to the XRAM chip, and it's 1 because it's positive logic, so we want to select it. The third bit is the chip select of the calibration RAM, and it's 0 because it's positive logic and we want to disable that. And the most significant bit corresponds to one of the lines in the data acquisition boards on the device, which is not relevant to this story. So now we're back looking at the unit, and we see this is the first I/O expander, and this is the shunt, the bridge that connects the data and address bus, and I've used that as a convenient place to attach my wires. This bunch of wires, it connects my logic analyzer to one of the RAM chips so that I can see the address bus driving the chips. And well, there are other miscellaneous wires here and there for chip select and for the address latch enable and so on and so forth. This is the address bus, the 8-bit address data bus. This is the 4-bit control bus for the I/O expander, and on the side I have a bunch of control wires, chip select for the ROM, read write for the chips, the address latch enable, and so on. So the objective here is to write a program on the Arduino to allow us to exercise the different bits of this device and see what is happening. Why is this thing not responding? So we are selecting the calibration, the normal RAM, and we want to run a read-write test on the RAM to see if it works. So let's look a little bit further. The green line here is the address latch enable. So here we present an address to the bus 01, and we pulse the address latch enable so that this is transferred to the address bus lines. These are probes connected directly to one of the RAM chips, so we see what address appears on the address bus. So we are looking at the output of the address latch, and here we see that the moment we pulse the address latch enable, the 01 gets copied to the address bus. So we are selecting address 1. Here we want to write 01 to the RAM, so we pulse the write pin, so the 01 gets stored in the RAM, and then we pulse the read line to read the data. The address, as you can see, is the same. So let's go a little bit in, and we read OF. Oops. And unfortunately, this is the same story continues as we go along. We write 2, we read 0F, we write 3, we read 0F. But as we go down, we see that while the least significant nibbles are always F, the most significant nibbles actually work. So we are lucky in the sense that only one of the two RAM chips is actually gone, and that means that once I replace it, the unit will be in a better shape. I hope that that'll be the end of the story. Now, before I go away, let me show you another thing that caused me a lot of anguish, and it's this one, this chip. You can see it's socketed, and it is socketed because I had to replace it. This is the address latch, and unfortunately the old one is the one I had to remove, and it was not working. And by the time I found out that I wasn't driving the bus, I had spent a lot of time essentially wasting my time trying to find digital signatures for with the signature analyzer of the ROM and RAM chips, and that didn't obviously work because they were always latched to address FF. If you want to have a look at the program that I wrote for the Arduino, I'll post that on my website. It's not a complete program. It doesn't have a user interface. Essentially, the main loop has statements that are either commented out or compiled in to activate different diagnostic checks. I was hoping one day to expand it so that it becomes more interactive. So by the time you get the logic analyzer set up, the program has downloaded to the Arduino and it's running. So I didn't put a lot of effort in the interactive aspects of the program. This particular test is printing the contents of the calibration RAM, and it is running a read-write test on the XRAM, and this is where we see that while the least significant 4 bits are always F, the most significant actually track the address. So essentially I'm writing the address to the position, so I can see that the high order bits track the address, while the least significant bits don't. So the one of the two XRAM chips is not working, and once I replace it, I will be able to continue testing. Thank you.